Great. Hey everyone, I'm Mike. I run an experimental game studio here in Berlin, and I'm here to talk to you today about my practice as a game designer using JavaScript to make games and installation art out of weird hardware and vintage electronics. Specifically, we're talking about this hardware, which is a Western Electric 551A PBX telephone switchboard from 1927. I'm sure everyone in this room is very familiar with the Western Electric 551 line, but in case you need a refresher, the 551A is the smallest one they made. The B is the next one up, which is literally 3 of these next to each other, which would have been used by 2 people. This one would have been used in a hotel or a small office. You'll be able to see it a little better on the next slide. This specific telephone switchboard was in use at the Mead Paper Mill in Chillicothe, Ohio in the United States, where it was in use for about 40 years, probably by the same person the entire 40 years, which is its own ridiculous story that we don't have time to get into because we're here to talk about its present, which is to play a game. So as a game designer, I make experiences that use non-traditional interfaces to connect people to the world around them and foster a sense of intellectual curiosity. So this is a game that came out of funded research I was doing at the MIT Media Lab. It's called Hello Operator. So you sit down at this game and use this hardware as if it was your day job. People want to make phone calls, and you have to connect them to each other and connect the cables the right way. And in doing so, you will actually learn how to use this hardware as if it was the 1920s. Like, there are obviously some concessions made for the sake of making a fun game, but as it plays today, you could actually read the instruction manual from the 1920s, and from those instructions know how to play this game. It's what's known as a time management game, coming out of this rich tradition of casual games such as Diner Dash that are generally all about like taking some sort of service job and giving you a sequence of steps to execute, whether it is seating people at a table at a restaurant, then taking their order, then bringing their food to them, or the steps needed to connect a phone call, and making that part of the gameplay. And executing a single series of steps to help one customer is very easy. Managing 10 people at once who are yelling at you that you haven't connected their phone calls yet gets very hectic very quickly. So we'll touch a bit more on that game design aspect and why of things later. For the most part, this talk is going to be 2 different parts. The first half is going to be looking at, so okay, you've just had 100-year-old hardware show up on your front doorstep. If you're a programmer and more of a software person than a hardware person, how do you actually make sense of this? Sort of what is the process of figuring out how to deal with hardware like this? And then we're going to talk a bit about both the software and the game design side of things and talk about, sort of spoiler alert, the game engine that runs this is sort of the small JavaScript sort of business engine, if you will, that sort of knows how to manage the state machine of the game. And then it has front ends that mean I can play it on the physical switchboard. I can also play it on an iPad. I can play it on a command line or in unit tests. And we're going to talk about the game design decisions and software engineering decisions that led to that let me sort of design a functioning design process for making hardware games like this. There's a little more video. So we bought this thing on eBay. Someone in Ohio built a crate for us and had it freight shipped to us for more money than it cost to buy the thing in the first place. What would we do with it then? Like, this is very, very heavy, very confusing. Where do you even get started? And that was the first problem. So it was very easy to open up the back and see sort of all the cabling that was there, but you probably can't really make out here. On the front there's actually a keyhole. That front panel is supposed to open up to reveal all of the cabling and wiring for those lights and those switches. And that keyhole was locked. And we went onto eBay and talked to the person who we bought it from, asked if they had a key. They didn't. We bought a different key that looked pretty similar. Couldn't get in. Like, we were at MIT, there were a lot of people there who know how to use lockpick sets. No one could get in. We ended up having to cut through this piece of sheet metal in the bottom just to get to it and sort of cut through it and unscrew it and remove it. But I'll digress quickly. Sort of, I think the coolest part of this project that I can say, because I was not responsible for it, is one of my colleagues in the project looked at the lock and said, "This is really simple. I know what to do with this." He grabbed a set of calipers. He did a little bit of 3D modeling. And here is the metal 3D printed key that we had printed that actually fits the 1927 lock and that we still use today. So that's really cool. But okay, even after we got that open, this is what we were looking at, which is pretty intimidating. So to step back, the way this thing actually works, so if you want to connect two people who want to make a phone call, if you can see there on the front, you can sort of imagine all of these cables and lights and switches as columns. Each column has two cables, two lights, two switches. And within that, there are sort of two different pairs. So you have one set of a light, a switch, and a cable, another light, a switch, and a cable. If those two cables are plugged into two different ports, conceptually those people are talking to each other, and the switches go two different directions. If you push them away from you, that means I am talking to the person on the other end of this line. If you're pulling it towards you, that means I am ringing that person and they're going to hear the telephone ring. So if you've done any sort of hobbyist electronics, a lot of this sounds like it's pretty straightforward. An LED is pretty simple to make a light turn on. A switch that starts out neutral and can go one of either two ways is pretty simple. You have probably 3 pins coming into it, maybe 4. When we open this up, we see this. There were 7 different pins coming out of each of these switches that you would expect to have maybe 3 or 4 pins coming out of them. Each of those pins had 7 or 8 wires attached to it, and it was duplicated, so there were actually 14 pins. And when we started measuring it, they activated in really weird circumstances. So one of these pins would connect to ground and complete a circuit momentarily while you were transitioning between states. Which again, if you have done any modern hardware, that's not really the way you do things. That doesn't make any sense. But it turns out you do things differently when it's the 1920s and all of your logic is based on physical relays. And if you need something to fire in between when you are transitioning states, maybe it's easier to have that be caused by a physical metal plate momentarily touching something else. If you need that piece of data to be used in a dozen places, maybe it's easier to run a dozen lines through it than it is to figure out how to multiplex it using like gigantic relays. Which is tricky even if you're an electrical engineer. I am not really an electrical engineer, but even these technical manuals we got from the 20s, when I asked my friends who were smarter than me, no one knew how to make sense of any of it, which points towards sort of the #1 tool for all of this, which is the multimeter. This is sort of the equivalent of console.log or debug print statements, but for hardware. For most of this, we honestly just use a continuity tester, which is you have 2 pins or 2 alligator clips. If they are touching each other or a circuit is being completed, they will beep at you. So there's the slow, methodical work of taking 2 pins on this gigantic, confusing switch, attach alligator clips to them, figure out how to make that circuit complete, repeat ad nauseum until we know what everything does. Slow, methodical work. I'm not going to go through this process for everything, but the back was pretty much the same thing. There were all these wonderful things to explore, like those individually lead-weighted cables, so you could drop the cable and it would fall back into place. We had these delightful, all of the things in the back, they were connected via the sort of cable management where all the cables are individually waxed and tied together in these structures that I have been told we just don't know how to do that anymore. That may or may not be true. But similarly, all of these cables in the front, the ports, they look a lot like standard 1/4-inch audio jacks. They're a little bit different. But you would expect the cables have 3 different connections coming out of them, 2 data connections and a ground. And yet these connectors in the back had 5 pins coming out of them. And those 5 pins didn't connect anywhere sensible. They connected up to these gigantic pin blocks that weren't wired up in ways you would expect. And again, there was no real unifying theory of how to do this other than slow, methodical work, making sure that you're checking your work and that everything you're doing seems to work. The other last little story I will tack on here is those lights on the front. Those were not LEDs originally because it was the 1920s. They were these beautiful, tiny incandescent bulbs that we are not using. They all originally worked, but it would have been a pain to wire them up, and if one of them broke, it would have been a hassle. But they were connected via these gorgeous hand-carved wooden sockets. Which of course we had to use those. We could not use those. One of my colleagues was gracious enough to spend hours desoldering all the original LEDs, or the original lights, and put these LEDs in instead. But that meant, so if you're doing modern electronics work, you will often use these things called neopixels or other sort of multicolor lights that are daisy chainable, meaning sort of a standard LED has 1 pin coming in that's data, or energy basically, and one that's ground that you sort of comes out of. Like these here, those had 2 connections. But that means that for every single LED, you need essentially one data pin, which if you have 50 plus 20 is 70 LEDs, that's a lot of data connections. You can get LEDs that'll let you have an arbitrary number of lights off of only 3 different data pins. But we had these beautiful hand-carved wooden sockets that only had 2 pins coming into them. So if we wanted to use these, we couldn't use those. And we could say, fine, that's a worthy trade-off. We want to use modern like RGB LEDs instead, but then we would have needed a different way to connect these LEDs into the switchboard itself, which sounds like a much larger problem. So we ended up settling for, it's fine, we will just use the regular LEDs and it's gonna be a pain. Which is a thing that carried through to everything else. So if you've ever done any sort of hobbyist electronics work, an Arduino has about 15 I/O pins. A Raspberry Pi has 20 something. So the switchboard has, on the top, there are 50 different plugs. There are 50 different LEDs. This front panel has 20 cables, 20 LEDs, and 20 switches. There was also a rotary dial we had wired up at one point, and we put a little magnet and a magnetic sensor in so we could tell when you hung up the phone or not. That's a lot. And that's also not a scale that sort of most people doing hobbyist electronics are used to dealing with, not something I was used to dealing with. One of my electrical engineering friends recommended sort of an industrial grade prototype board that I took it from him. I downloaded the Windows only compiler, I set it up, and the Hello World example did not compile. So we knew that we wanted to do something more custom. Sort of the lab I was in at MIT was very much into old school microcontroller fabrication, where sort of they don't really believe in Arduinos. It's very much you're taking these surface mount chips and designing your own boards and manufacturing your own circuit boards and soldering them. They had chips in stock with 50 I/O pins that were really not meant to be soldered by human hands. I did not have the skills to solder them. We ended up going to our local electronics shop, and we could buy Arduino Megas, which have 50 I/O pins each, using that same chip for about $10 each. So we ended up having 4 of them, which gives us 200 I/O pins, and we made these little Arduino shields that give us quick cable disconnects, which led to its one other problem, which is, so if there are 50 I/O pins and there are 50 plugs on the top and 20 cables, that means that the cables and the plugs are not on the same physical Arduino. And the way we needed to detect how one cable is plugged into a port, because we don't just need to know, like, this port has someone plugged into it, we need to know which is plugged into which one. We were doing this sort of port scanning technique that if you've ever made your own mechanical keyboard, this sort of technique might be similar. Basically, all of the ports were configured as inputs, all of the cables were configured as outputs, and you can sort of loop through all of the cables and say, all right, this frame, I'm going to send a low value along this cable and see if any of the inputs change and loop through that, which is very easy if you're running on one microcontroller. If you now have to divide those inputs and outputs across 2 microcontrollers, there's a little bit of complexity in terms of synchronizing the timing between these microcontrollers, which is a solvable problem, but is very different from making a fun game. Like, I set out to say, let's make a game that'll let people feel like they're a switchboard operator, and now I'm deep in the weeds of synchronizing microcontroller timing in order to, I don't know. But so all of this, I very consciously focused on how can I tackle all this hardware as its own problem so I can do the design space of making a game and building software in its own thing. Because the other sort of complexity modifier being added to this is this physical hardware showed up about 3 weeks before I needed to mail it out to the Game Developers Conference in San Francisco. So this was sort of an unhealthy, not something you want to repeat crunch period of, I have 3 weeks, how do I get this hardware working? Which meant that given I had a couple months leading up to that, and then a couple weeks after that before the show, I really needed to be able to work on the game itself without the physical hardware. So all of this work needed to be perfectly compartmentalized. So the thing to me about software is the feedback cycles are so small. Going from having an idea to seeing how it works is unlike a lot of other media you can work in. If you are working in hardware, things can take hours to days to weeks. Me going downstairs and fabricating another circuit board would take a couple hours to mill it and solder it. If I was having those done externally, that would take me a week or 2 if I was lucky to get new boards in. That's not great, whereas software can be instantaneous. So I partition this out into what are the different things I want to test, what are the different feedback loops I can design, what are the right different levels of abstraction to be solving different problems. So at the lowest level, there is this question of, does this piece of code actually do what I want it to do? Which we can do that really quickly. Unit tests are great. It meant that for things that were unit testable, I wanted to be able to write those. A lot of things about game programming are not particularly testable. That's sort of its own separate talk. But it meant for a lot of things, I wanted to be able to play the game as quickly as possible with as little context shift as possible, which for me meant I wanted a version of the game that I could play at the command line. So you can see the sort of text adventure version of the game where I could type something to simulate plugging a cable in. And so having that from day one was super important. It's easy to write automated tests to see if a game works. It's a lot harder to write a test about whether a game is fun. Really, the one tool we have for that is playtesting. But playtesting is really hard. It is a pain to convince people to come play your work in progress game. It is especially hard if you can't go to playtesting events or go to where people are to have them playtest, which is difficult if you have 80 kilograms of hardware that people need to come to you to test the hardware. So I knew that I wanted a version of the game that could run on an iPad, which felt like the right compromise of like being able to drag and drop on a touch interface is something that people will understand and still approximates what is it like to play this game, but would fit in my backpack and let me fit in playtest whenever I could. I didn't have a good screenshot of the iPad app because it used Swift back before Swift was Swift was not very stable at the time, but you can almost see it in that screenshot there. There's an iPad sitting on top of the switchboard. So it was easy to test things like, is this gameplay fun on an iPad? Like you're giving people a play test of, here is my time management game, but that doesn't test the experience of sitting down and playing with this 100-year-old hardware. For the onboarding, for example, it was easy to teach people, here are the series of steps to execute, but it's one thing to tell people this ugly gray box represents a cable, you can drag it with your finger, versus someone sitting down at the switchboard is going to be incredibly stressed out and scared by this giant piece of wood and metal, and they need to be taught that it is okay to experiment and it is okay to fail, and both it is not going to hurt them and they are not going to hurt it. Which meant like that on the rare occasion I did have someone who could actually test the game on the physical hardware, I needed to be able to do that. So whatever infrastructure I had to get this game running both on an iPad and in test and on hardware, it needed to be deployable at any given time to the hardware. I always needed to be able to run the latest version of the code on the hardware without any trouble. So the answer, like I describe it as the adapter pattern, even if you're not familiar with it by that name from the Gang of Four Design Patterns book, you're probably roughly familiar with the general concept. So instead of the game directly talking to some Arduinos, there was sort of a shimmed out interface that the game knew, all right, here's an object I will be given that I can tell to turn on a light or blink a light, and it'll tell me when some cables have been connected. And it doesn't care whether turning on an LED means an actual LED turns on or a UI view on an iPad changes colors or something gets logged out, which is great because that means, like in this case, I was using TypeScript, which meant it could run anywhere the game can run JavaScript. I could have that fake adapter for test. I could have the one for the console, one that was written in Swift with JavaScript core bindings for an iPad, and we could safely separate engine development from hardware development, which for a lot of people in this room doing sort of web development or other forms of professional software development, these are concepts that seem very similar to you probably. You're used to some flavor of separating view state from model state, whether you think about it as model view controller or React style view as a pure function of state and unidirectional data flow or solid object-oriented design principles. These aren't things that really exist in either games or hardware. I think there is a lot you could talk about the whole culture of games engineering, but at a basic level, both games and hardware traditionally have very serious performance constraints. If you are writing microcontroller firmware, you are often focused on how much space is the representation of my code taking up, how many variables am I assigning. Similarly in games, if you're doing 3D work, if you have a 3D renderer and a physics engine, you need everything you're doing with all that very complex math to happen in a single update loop, which needs to happen 60 times a second. So if your core update loop doesn't run once every 60th of a second, you're going to drop frames, and that's not going to be good. With any problem space like this, that is going to make it very, very difficult for you to think in higher abstractions and think about how can I make my life easier as a designer and as a programmer, because you're too busy making life easier for the computer. But in my case, I didn't care about that. Like, I could have gotten this game running on one of those Arduinos, probably. But we had a Mac Mini lying around the office and plenty of space in the back of the switchboard. Even if not, a Mac Mini is like 700 euros. An Intel NUC is a couple hundred. A Raspberry Pi is 40. A Raspberry Pi Zero is like 5 euros. And like the whole thing probably could have run on one Raspberry Pi Zero if not for the I/O problem. So there was no reason not to just throw computing power at this problem. I was not making a complex, fancy three-dimensional game, which I think is another design philosophy of mine that came from doing web development work, particularly for early-stage startups. If you have a web product and you have lots of users, which is a great problem to have, and your servers are falling over, if you are a large company, the obviously correct thing to do is you hire engineers who can solve your problem and make your servers scale. If you are very, very small and scrappy, you could do that. You could also pay your provider, whether it's Heroku or Amazon or whoever, a little more money for another server. And that's probably not going to scale in the long term, but for now, short-term throwing money at the problem means you can focus your limited resources, which is developer time and focus, on things that are more important. So similarly for me, throwing computing power at this meant that I could spend my time using a web technology stack that I was used to. It meant that I could think in higher level abstractions that let me do these other things I needed to do for my design process. That was phenomenal. Those 4 $10 Arduino Megas and this Mac Mini solved that. I could write software that was optimized for ease of debugging and playtesting. It let me spend more time being an artist and a designer rather than an electrical engineer or an embedded systems programmer. And similarly, this is where being able to write in TypeScript was really great for me, because it's a language that I know much better than if I'd been writing the game in Arduino C. I could have done that. I would have been a lot slower. And for all of this, like I'm talking about cross-platform code, it doesn't really matter that it's JavaScript. I happen to know JavaScript and TypeScript pretty well, but again, because we're not dealing with a physics engine and a 3D render and all these traditional games things, anything that runs cross-platform would have worked equally well. In my case, most of the other work I was doing in JavaScript, which had other benefits. So this was, while I was doing games research at MIT, this was all my side project. And the main project was location-based storytelling. Sort of without getting into it, I was making these sort of location-based interactive radio plays that changed what would happen based on where you walked or what the weather was like or all these other factors. So I had this JavaScript-based interactive scripting language that I wrote that let you vary a script for the sort of interactive narrative flow based off of arbitrary data sensors, which I'd been using for things like smartphone GPS as inputs and text-to-speech as output. But given that it was all in TypeScript, when I needed to design a tutorial for the switchboard, it meant that I had this tool in my pocket that I could pull out and use the same narrative engine, but instead of the inputs and outputs being things in your smartphone, the inputs could be plugging cables in and flipping switches, and the outputs could be audio files being played out over the headset. So you can see here, this is sort of my custom scripting language, what the actual interactive tutorial for Hello Operator looks like. If you're interested in that, I think slides will be available later. All of that narrative stuff is available on GitHub if you're interested in making that sort of game. Another benefit of working in the sort of shared ecosystem that I was familiar with is it meant that when I had problems, it was easy for me to come up with novel solutions. So the first time we showed this game at GDC, it turns out the switchboard really didn't like being flown across the country. And the first day, we had a lot of bad reliability problems where the things that were actually happening on the physical hardware did not match up to what was happening on the internal state of the game. And we didn't really know how to debug it. Like, there was a computer in the back, but I wasn't going to sit there watching what was happening while people were playing. But I realized we already had this concept in the game engine of, well, the game has an interface to the outside world that in this instance is the physical switchboard hardware. It's not hard to make it, let it accept multiple adapters instead of just one. And we already have this functioning iPad version of the game. Because of all of the work I had already done, it was very easy to make it so I could add a second adapter that just opened up a WebSocket connection to an iPad version of the game. And in an hour or two of work, I had an iPad app that I could hold in my hands and see wirelessly what the game running in the computer thought the internal state of it was. And I could switch things around and tap on things to make the internal state match the external state. And if I hadn't made all these earlier design decisions, maybe I could have done it in a longer period of time. More likely, it wouldn't have even occurred to me. But having already made these decisions to focus on, well, how can I make designing this as easy as possible, made things like this relatively trivial. And so everything I'm saying, I'm talking about making this specific hardware installation. But I think this really applies to any sort of game that deals with non-traditional interfaces and doesn't feel like pressing the A button to jump. So this is a game I worked on called When in Rome. This is a board game that you can buy on Amazon, but it requires that you have an Amazon Alexa device. And so it is a travel trivia game where you're flying around the world, meeting people in new cities, and Alexa is acting as sort of the game show host, and you're hearing real recorded audio from people who live in those cities. And so if any of you have done any sort of voice skill development, generally these are web apps. You have a server that Amazon will send web requests to, and you'll respond back with a payload that'll result in someone's Amazon device saying something. Google and other voice platforms work relatively similarly. And I took a similar approach here. So the game itself didn't know about Amazon, didn't know about running an Express web server on Node.js. The game's API, as it were, was the single function. There was sort of a pure function that says, all right, you're going to tell me what the user has told you to do, which in our case was coming straight from Amazon. You're going to give me some data that represents a game state, which we were loading either using Amazon session data or from our own database. And you're going to give me an output object, whether you want to think about it as sort of a Haskell monad, or if that scares you, like before, just a bundle of functions that knows how to do things, and it's going to be able to mutate the outside world and construct a response to the player based on that. So we have this nice, pure thing that represents a game that I could easily write unit tests against that. I could easily debug it locally, because Amazon doesn't give you great tools for testing Alexa skills without physically talking to an Alexa device. But it meant that we could also very easily have this sort of exported JavaScript API wrapped in an Express app that talked to Amazon, which also meant that, like, in the future, if we want to port the game to Google Voice or Siri or whoever, that'll make it very easy to do. So we've gotten pretty deep in the weeds. I want to take a step back and ask why all of this is even worth doing. I'm the first to admit this is all a major pain. I've spent so many hours poring over this hardware that for a year was literally sitting in a basement at MIT and is now sitting in a storage locker in New York. Why even bother with hardware? And for me, what is magical about this and other projects I've done like it is when people come up to it when it's being shown, whether they are people who normally play games or not. There are people who would clearly not really want to go to a telecommunication history museum and actually learn about how this works, but they see this giant piece of hardware and say, this is awesome, I have always wanted to know how this works, and they will spend 20 or 30 minutes being deeply engrossed in this very, very difficult experience on the middle of a noisy show floor. And to me, that is phenomenal. It's sort of, I don't want to use the word gamification because that has a lot of negative connotations, but it's sort of the good form of gamification. If it was a little more didactic and you felt like you were being taught to, it wouldn't work and you'd be scared away. But part of it is you're learning this real world skill, which is intrinsically fun, but you know it's an obsolete and useless skill, which makes it fun and playful and a game rather than a chore. But even as I've disarmed you and taught you, like, oh no, don't worry, we're not actually teaching you, we are secretly teaching you something about the past, which is awesome. But even stepping away from physical hardware, vintage hardware rather, and like teaching people about the past, this may seem kind of obvious, but the way you physically interact with something meaningfully shapes your response to it. You feel, even at a basic level, you feel differently about using an app on your tablet or your phone than you do using the same service on your desktop or laptop. You even feel differently typing on a MacBook Pro's clacky butterfly keys versus using a mechanical keyboard with juicy cherry switches. And that level of interaction and tactility matters. And as an artist, having that wider dynamic range to work with of like what is the emotional response being evoked by the way players are physically interacting with your system, that is a really cool thing to play with. But also, okay, sure, a lot of you in here are probably here at this conference because you are interested in building software. Maybe it is your day job. You don't care about artistic expression as its own ideal. I would argue that point, but we can talk about that after this talk. But learning how to work in other forms of engineering is super useful, even if you're not going to do something as huge as this, like getting an Arduino breadboard and plugging some stuff in without doing any soldering is going to teach you a lot about other types of engineering that'll color your day-to-day job programming. The way you think about testing and testing software might be shaped if you have to do a literal smoke test, where after you've soldered a bunch of stuff, you plug it in and make sure that it doesn't literally physically smoke and burst into flames. You're used to maybe like making some changes really quickly and hitting save, and by the time you go back to your web browser, Create React app has already live reloaded your changes. If you have to spend 4 hours fabricating a new circuit board every time you put the traces a little too close together, that might give you a little more appreciation for what you have, and maybe even give you a little more discipline when trying to do things for the first time. But also, finally, I'm being selfish here, which is I want more people to make more cool things in the world. I assume a lot of people here got into software because there was something really cool they wanted to make, and so they learned how to make it. And I think hardware is often scary and seems unapproachable, but it's not. And I think you will have to learn a bunch of things that you don't already know, but I think a lot of the work that I do goes to the point that you can use the software skills you already have. You don't have to immediately drop into learning like 8-bit microcontroller assembly in order to make something cool happen with hardware, which can make it a little easier to get into that, which means you should and make something really cool. And that's all I got. Thanks.
I think we have a few minutes for our questions. Are there any questions? Oh, there's one over there.
Yeah.
Hey, so you're like advising to get into this kind of old obsolete machinery and learn how the past things were done.
Mm-hmm.
Would you also continue doing this yourself? Like, would you continue developing things for old machines and trying to learn how a user would experience with this?
Yeah, totally. So this was, I didn't talk about, this was the second game like this I've made. Before this, I had a game where you were a telegraph operator with 19th century Morse code hardware tapping out telegraphs. And I still actually sell on Etsy USB telegraph keys. So if you tap the Morse code for the letter H, it'll type the letter H into your computer as if it was a keyboard. And like I've poked around with other things like teletypewriters from the 60s and 70s and more early digital computer stuff. But I think there is a tricky hard break where things like this, it is very easy to ignore a lot of the wiring that is there and connect it up to modern electronics. Whereas once you get far enough into the present that you're dealing with digital computers, it is difficult to ignore it, but dealing with it gets very tricky because now you have to get 2018 hardware to interoperate with like a 1980s computer.
Thanks.
Any more questions?
Yep.
First of all, thanks for the talk, super inspiring. Yeah, about the, I noticed that some articles talk about that the future of the interactions will be like invisible UX. Mm-hmm. And I was inspired by the Alexa game that you were talking about. Do you really think that we are going in that direction? Will be feasible? It's a thing that's going to happen?
Yeah, I think it is. I think it is hard to say how things will actually go, but I think in general, like the best design is one that you don't notice. And things like telling Alexa or some other voice UI something you want to do is interesting, but that is less interesting than the computer already knowing what you want to do or inferring from context what you want to do. I don't know the path to get there because that is very difficult, and sort of AI as we know it now isn't good enough. but I think that is definitely the pie in the sky goal. I think like one of the things that I love about doing this sort of games work is historically a lot of major changes in UI happen to come from games and the sort of experimentation of what does playing in a new interaction paradigm tell us about that interface.
More questions? Behind me, yeah.
Thanks. So I think I missed the first few minutes, but do you do this for a living? Or
Yeah.
how do you get paid for this?
Yeah, so this project in particular, I was doing funded research at the MIT Media Lab in Cambridge, Massachusetts. Right now, I'm running my own game studio where the stuff we're doing isn't quite this experimental and less arty, like we are working on things that we will sell that people will hopefully pay us money for. But it is still in the same vein of how can we use non-traditional interfaces to sort of connect people to each other and the wider world instead of just making violent shooty games, although those are great too. It's how many people? It's a one-person game. Like it is all there are people you hear voice recordings of people who want to talk to other people, but that's all the computer. If it was in a place where I could work on it, we'd originally planned on having a larger narrative arc. So as you're listening in on people's conversations, what are the stories you're overhearing? Do you have choices to make of, that someone wants to talk to someone they're having an affair with, do you connect them to that person or do you connect them to their partner? Or like espionage thriller type stuff. I think there's sort of a whole bunch of directions you could go with thinking about the stories you're telling, listening in on people's conversations.
Yeah, so now we ran out of time. So thank you for
Thank
your
you.
talk.